Section 5, Part 3, we want to talk about the standard deviation of a random variable. So whether you've got something that's really skewed like this, or kind of skewed, like, well, very lopsided anyway, like this, or something more like this, or something that is very symmetrical. Nevertheless, we can talk about the standard deviation of a random variable, which is what the standard deviation always is. It's the average distance from the center. The center being the balance point, the mean, mu of x, as previously just computed. The standard deviation of possibilities, the standard deviation of a random variable, as distinct from the standard deviation of so many numbers, S, section 2. The standard deviation of a random variable is the average distance from its balance point. On average, how much more or less than 3.5 is your average roll of the die? How much more or less than 50 cents is your average lottery ticket? How much more or less than 0.4 is your typical group of 4? How many more or less than 0.4 lefties is your typical group of 4 going to give you? So, given that the balance point is 50 cents, how far away from that do we tend to be? Given that the balance point is 3.5, how far away from that do we tend to be? Given that the balance point is, what do we say, 0.4, how far away from that do we tend to be? And you can see from the area that, you could have something with a balance point of 0.4, but theoretically you could tend to be very far away from it. Take this example here, If this thing had this pyramid shape peaking at 3.5, 2 bars, smaller bars, but still symmetric, then it would still balance at 3.5, but on average you would tend to be closer. On the other hand, let's say it had a big valley in the middle. Bar, 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 symmetrically. Then it would still balance at 3.5, but on average you would tend to be very far from 3.5. So the standard deviation is just as important as the mean. Like I said, the average human being has one ovary, but the average human being has one more or less than one ovary. That's just as important. The average human being has one ovary. The typical human being does not. The average roll of the die is 3.5. The typical roll of the die is not. The average lottery ticket is worth 50 cents. The typical lottery ticket is not worth 50 cents. So just as important as the average, the balance point is how far away from that average you tend to be. And that's the concept of the standard deviation of a random variable. Now, before we talk about the formula, first of all, the concept of the average distance from the center makes sense whether we can compute it or not. In other words, we can and will talk about these ideas for a continuous random variable. But for a discrete random variable, we have a formula for it, just as we did for a discrete random variable for the mean. You can always talk about it, but if it's discrete, you can compute it the way we've been computing it here. Of course, there's 3 possibilities, right? There could be 5 columns, or there could be an infinite number of theoretical columns, continuous. That doesn't make any sense. You can't compute that. Or there could be 5,000 columns, so that if could would, you could theoretically compute it, but you're never going to. So it can play out in all kinds of ways, and the theory will be true regardless. But for a discrete random variable, it works out to the following formula. So before we talk about that, there was an idea in the back of my head. What was it? It's gone. So let's just go on to compute the standard deviation of a random variable. Now, as with S that we talked about in section 2, there's 2 formulas for standard deviation. There were 2 formulas for the data standard deviation, S, in section 2, one that I gave you and one that I did not. And it's the same thing here. There are two formulas, one which I will give you and one which I will not. So once again, this is the computational version of the standard deviation formula. There is another version of this formula which algebraically is 100% equivalent. It involves subtracting mu from each possibility and again working in columns. But again, unless the average is something nice, that could get very tedious very quickly. And if it's really ugly, if it's a repeating decimal or something, then you could be losing accuracy in the middle of the problem. So this is the easiest way to compute it. It's very similar to what we did with our formula for S. Oh, and there it is. That was the thing I was trying to remember a second ago. Let me just digress before we do the formula. This is the computational version of the formula. It's the easy one to use. It's the one we will use. There are other ways if you've seen it in the past. The point in the back of my head that I was trying to allude to was this is a common mistake that students sometimes make. Why do we not divide everybody by 4? Or why do we not divide everybody by 2 or what have you? This is a common mistake that students make in these formulas. Why do we not divide everybody by 6? Well, in a sense, we already have, right? 1 plus 2 plus 3 plus 4 plus 5 plus 6, all divided by 6. You see, multiplying by this takes the place of the division, right? We talked about this in the previous thing here, right? Multiplying everybody by its probability is effectively taking into account the total. I talked about this problem early on in the beginning. We have a sleight of hand going on here. In previous sections, we have used n for the number of pieces of data we have, which here would be 6,000. But in this section, we're using n for the number of possibilities, which is 6. You don't want to mix up the one with the other. So the bottom line is when you take the data average of 10 numbers, add them up and divide by 10. Mathematically, that's the same as multiplying each of them by a tenth, right? Again, we're just breaking up the fraction. In other words, you're weighting them the same. 10 numbers, each of which has weight 1/10. So when you divide by the total in the data average, you are weighting them the same, which is exactly what we may or may not have here. In this case, we do, but it's all figured in already, right? Likewise, here we don't divide by 10 or something, or 2, because it's already taken into account, right? 0 times 95 over 100 plus 10 times 5 over 100. That is to say 0 times 19/20ths plus 10 over 1/20th. There's 19 times as many zeros as there is ones. You're not weighting them the same. With all that in mind, if we go back to the data standard deviation formula, it's got this dividing by n and dividing by n minus 1 thing going on. Well, the dividing by n business only comes up in the computational version of the formula. It was part of our shortcut. The n minus 1 is inherent in the formula no matter which version of this you use, and we went into why it's n minus 1 instead of n. But the point is that the division is weighting everybody the same. It's saying that the 2 is just as heavy as the 3 is just as heavy as the 5, and so on. What you've got to remember is that we're now not talking about data any longer. We're talking about possibilities. In the long run, you have 95 zeros for every 5 tens, and so forth and so on. So there is no dividing by the total. There is literally no total to divide by. You may or may not have any lottery tickets. These are still the rules. You may or may not ever roll the die. These are still the rules. Possibilities rather than data. So multiplying by the probabilities takes the place of dividing by those totals. And that's why these formulas work out the way they do. Whether it's mu or sigma here, which we're about to talk about, you don't have that dividing by the total thing going on. Other things take it into account. Now again, this is the computational version. As always, we use sigma or S for standard deviation, S for the standard deviation of so many numbers, what we were just talking about in section 2. These numbers have the standard deviation below 5.3 something. The standard deviation of possibilities is a more abstract concept, so we use lowercase sigma. Remember, that was capital Greek S for some, which I am unable to highlight here, but capital Greek S for some, lowercase Greek s for standard deviation, for an abstract standard deviation, the standard deviation of possibilities. So the easy way to do this formula is it's the original mu of x that we've just computed, square it, and subtract it from the mean of random variable x squared. Let's think about that. If x for the die can be 1 or 2 or 3 or 4 or 5 or 6, then I'm just of two minds here. What's going to happen if I try to finish uploading this video? Okay, it's not going to make me stop here. So let's do that for time reasons. So I'm just talking while I finish uploading this video. And I'm still recording, so we're good. There is no pause on this silly thing, unfortunately, because of course there isn't. So here we are. So where was I? Random variable x squared. Suppose you're talking about the die. If x can be 1 or 2 or 3 or 4 or 5 or 6, then x squared can be 1 or 4 or 9 or 16 or 25 or 36. If x can be $0 or $10, then x squared can be 0 square dollars or 10 square dollars. If x can be 0 or 1 or 2 or 3 or 4 left-handed people, then x squared can be 0 or 1 or 4 or 9 or 16 square left-handed people, if we're following our units. So that's the idea here. It's not as complicated as it sounds. You just do the exact same calculation that you would have done to compute mu of x, except mu of x squared will be square each possibility. So mu of x squared is going to be 0 squared times this, plus 1 squared times this, and so on, and so on, and so on. And here it is for the die. So 1 squared times the probability of being in that situation, plus 2 squared times the probability of being in that situation, and so on, and so on, and square on, so on. Reality check, square the possibilities. Possibilities could be anything. 1, 2, 3, 4, 5, 6, 0 and 10, some negative degrees Fahrenheit, some other degrees Fahrenheit. The possibilities could be anything. The probabilities still have to add up to 1. Square the possibilities, not the probabilities. So for the die, it would be 1 squared times a 6 plus 2 squared times a 6, and so on and so on. Again, take advantage of the fact that they're all the same. 1 plus 4 plus 9 plus 16 plus 25 plus 36 divided by 6, 91 sixths. Now, I am deliberately not going to round that because I don't want to lose accuracy in the middle of the problem. The calculator can keep track of it. Internally, you can use the answer key button and so on. It's 51.66666 repeating. 51 and a sixth, probably. But call it 91 sixths. The original mean, 1 times a sixth plus 2 times a sixth and so on, we've seen was 3.5. So there it is. The original mean squared, subtracted from the new guy, take the square root. So 3.5 squared, subtracted from 91 sixths, square root. 3.5 squared is 12.25. Subtracted from 91 over 6, 91 over 6 minus 12.25, or answer in my case, is 2.9166666666. And then finally, don't forget to take the square root. Square root of answer is 1.707825128, irrational to the edge of the screen. Call it 1.708. Well, if I round what was just popped up on my calculator, that is to say, if I do exactly this calculation, I give up, but the square root. If I do this calculation, then round it to 4 places, I am going to get this. So there was no intermediate rounding in my case. There's no rounding error. I mean, it is true I rounded it up 1.7078 something, but it's accurate. Call it 1.7 for verbal purposes. The average roll of the die is about 1.7 more or less than 3.5. Let's go back to our picture of the die. Bearing in mind that we are talking about 1, 2, 3, 4, 5, 6, and height 1/6 for everybody. So your average roll of the die is dead center between 3 and 4, 3.5. Again, the scale here is not very helpful. 1, 2, 3, 4, 5, 6. So your average roll of the die is dead center there at 3.5. How much more or less than 3.5 is your average, let's say, typical roll of the die? Well, 3 and 4 are a half away, right? These two, 2 and 5, are 1.5 away. And these two, 1 and 6, are 2.5 away. So given that the center is 3.5, the closest bars are 0.5 away. The furthest bars are 2.5 away. Now the thing about an average distance from the center, I've mentioned before, is that it should be bigger than the smallest one and smaller than the biggest one, right? So the average distance from the center should be more than 0.5 and less than 2.5. So yeah, I may not have a lot of instinct for the 1.7-ish, but it is plausible. It's more than 0.5 and it's less than 2.5. What do I mean by that? It's the easiest thing in the world to forget to take the square root. Well, this is square die rolls or square dollars or square left-handed people and so forth and so on. And so is this. So I've got to get back to the right units. The square root takes me back to die roll or dollars or left-handed people or whatever. So it's important conceptually. But more than that, it makes my answer right? Before I took the square root, this was 2.9 something, which is not less than 2.5. It is too big to be an average distance from the center. So always ask yourself whether it's plausible. The more complicated a concept is, the more important it is to ask yourself whether the answer is plausible, right? I will buy in a general way that your typical roll of the die is 1.7-ish to either side of 3.5. Likewise, I've got an indication here. Given that the balance point was 0.5, 0 is a half away, and 10 is 9.5 away. So the standard deviation better be between those two things, even for something this cockeyed. For this, it was 0.4. So the 0 is 0.4 away. That's the closest thing. 1 is 0.6 away. And the 4 is, I don't know, 3.6, something like that, away from that center. So the standard deviation better be more than 0.4 and less than 3 something. And probably not particularly close to either, but let's find out. So always ask yourself whether an answer is plausible. If it isn't, you probably forgot to take the square root. If you didn't, you made a mistake somewhere else. What is the standard deviation of the number of left-handed people when picking 4 people? Well, remember that my mean was 0.4. My balance point was 0.4, so here it is again. On average, how much more or less than 0.4 is the number? If I pick 4 people and count the left-handed ones, how much more or less than 0.4 is it likely to be? It's probably nothing like 3 something, because this doesn't happen very often, but it's probably more than this would be. So let's check it out. Number 1, I will get the mean of x squared. Now the mean of x squared has no real world use. It's just an intermediate step to keep things easy on ourselves. It could be 0 or 1 or 2 or 3 or 4. So x squared can be 0 squared or 1 squared or 2 squared or 3 squared or 4 squared. Square the possibilities. The probabilities still have to add up to 1. 0 squared times the probability of being in that situation, plus 1 squared times the probability of being in that situation, plus 2 squared times the probability of being in that situation, and so on and so on. The bottom line is that'll be 2916 plus 4 times that, plus 9 times that, plus 16 times that. And it's exactly 0.52. So there it is. Let's scroll up a little bit. 0.4 squared subtracted from what we just got, and then take the square root. So let's do this slowly. 0.4 squared is 0.16. 0.52 minus 0.16 is 0.36. And in a highly unusual move, 0.36 square rooted is exactly 0.6. Of course, 99 times out of 100, if you take the square root, you're not going to get something nice. It'll be irrational. You'll have to round it. But this would be the exception. So there you go. Your typical, when you pick 4 people and count the left-handed ones, on average, you're going to get 0.6 more or less than 0.4. Now this is pretty cockeyed, right? This is pretty skewed. Here's the 0.4. Well, 0, 1, so let's call 0.4 about here. 0.6 will take me way over to here, right? If I go 0.6 on the small side of 0.4, it'll take me way over here. And there's nothing that far away. On the other hand, if I go 0.6 to the other side of 0.4, what is that? Probably 0.1, or actual 1. Well, there is stuff a lot further away than that. So even for something this skewed, it is still plausible as an average distance from the center. 0.4, 0.6 to this side of 0.4, there's stuff a lot further away. 0.6 to this side of 0.4, there's definitely stuff closer. So it is plausible as an average distance from the center. And let it be said that 0.36 versus 0.6, if you forget to take the square root, doesn't greatly change it. But if the original numbers for x were bigger, you'd see a bit of a difference, as we have before, between forgetting to take the square root and not forgetting. For example, let's look at the lottery tickets. How much more or less than 50 cents is your average lottery ticket worth? Well, let's check it out. So we found mu of x. It was 0 times 0.95 plus 10 times 0.05, which was 0.5. And here it is. So now if we go back and find mu of x squared, 0 squared times its probability plus 10 squared times the probability of being in that situation. 0 squared times the probability of a losing ticket plus 10 squared times the probability of a winning ticket. Now again, it's kind of important for the long run, more on this in the next section, that I can do this in my head, right? This is nothing plus 100 times 0.05, which is obviously 5. Why it's important that I should be able to do these two in my head, we'll see in the next section. And there's another typo, by the way. But it's 5. It's this minus the original mean 0.5 squared. So without the typo, lose this. It is 5 minus 0.5 squared, and then take the square root. Order of operations. 0.5 squared is 0.25. Actual 5 minus 0.25 is 4.75. And 4.75 square rooted is 2.179449472. Call it 2.18. So there you are. And as always, the standard deviation is in whatever units you had in the first place. 1.708 die rolls, 0.6 left-handed people, $2.18. By the way, why do I round this to two places? Well, at first glance, it would seem like a reasonable thing to do, right? We are talking about money, so to the nearest penny makes sense. But then you remember it's an average of many lottery tickets. So, well, it's an average distance from the center of many lottery tickets. So there's no particular reason to round it to two places after the decimal. You could have whatever kind of accuracy you wanted there. When I go to use the standard deviation a bit later, well, it's common sense. If you're going to end with a calculation, then you follow whatever rounding instructions you're given. If you are going to use it for something later, then it would be a good idea to keep as much accuracy as you can, right? But since I'm not going to use it at the moment, I'll just call it 2.18 for no particular reason. I'll round it that way and move on. So your typical lottery ticket is worth about $2.18, more or less than 0.5. Given that it balances at 0.5, which is one would be here, half would be about here. So given that it balances at 0.5, how much more or less than 0.5 is your average lottery ticket? Well, if you go $2.18 this way, if you go 2.18 this way, then there's nothing that far out, right? But on the other hand, if you go 2.18 the other way, there's stuff a lot further out. So even for something this asymmetrical, everything still is kind of balancing. It is an average distance from the center. Again, given that the center was 0.5, the closest thing is 0.5 away. The furthest thing is 9.5 away. So the average distance from the center should be more than the one and less than the other. And that is exactly what we're seeing. And if you had to guess based on the shape of this thing, you would say that on average you tend to be if you had to guess based on the shape of this thing, you'd say that the average distance from the center was going to be a lot more like 0.5 than it is like 9.5. Because on average, you tend to be closer, not further away, right? So given that one distance from the center is a half and the other is 9.5, given that the majority of the stuff is on the close side, you'd expect it to be closer to a half than 9.5. So as far as intuition, instinct, that's exactly what we're seeing. It's a lot more than a half, but it's closer to that than it is to 9.5. So everything kind of checks and balances out. There is section 5, a word on standard deviation. We talked in passing. It's a parlor trick. It is not something we're going to get a lot of use out of, about how to use the mean once it's been computed. The long-term average of many repeats, reverse engineer for the totals. You'll see some problems or afterthoughts of problems referring to that just for practice purposes, but it's not the most important point of the world. Probably about $750. It is true that it's vague. So we'll be much more specific about that in section 9. Don't worry about it yet. For the moment, it is a point in passing. It is a half-hearted attempt to get some use out of the mean once we've computed it. But bear in mind that the mean, the balance point, is something you can compute and talk about whether it is useful or not. With that in mind, we can compute the standard deviation of a random variable. And we've done it, and we've talked about some intuitive ways of thinking about whether the answer is plausible or not, but we haven't done anything with it, right? So we haven't talked about what the standard deviation of a random variable will be useful for. I assure you, if you are running a casino in Las Vegas, then you not only want to know the mean winnings, but the standard deviation of the winnings for a game of chance, because as we'll see in the future, it is very, very important. It is just as important as what the balance point of the random phenomenon is how far away from that balance point you tend to be. A lot more on this and unit changes in particular in the next section. But just bear in mind that we haven't talked about what the standard deviation of anything is really useful for yet, apart from one particular context in section 3 when we divided by it. Scusi. So, sorry if there's dogs barking on the video. Let me just say that nothing will ever get done if you wait for perfect conditions, and leave it at that. So although we have computed S in section 2, although we have computed the standard deviation of a random variable here in section 5, nevertheless, we haven't really talked about what the standard deviation is ever used for, apart from the one specific context of the normal distribution. So maybe you can think about how all of this is going ultimately to fit together, but if you can't, let me just go back to giving you a little context on this, and we'll talk about that in sections 7, 8, and 9. The standard deviation was very useful when things were normal shaped. Otherwise, it is just something we can compute, and it doesn't necessarily have any real-world meaning that we can really talk about, apart from the visual interpretation of the average distance from the center, which we kind of beat to death. Okay? So it is one thing to be able to compute something. It is another to see what it is useful for. This all goes back to this statement that if you roll a die many times, you'll probably get about 3.5. How many? How probably? How about? Well, for the moment, it's a true statement, but it's a little vague. In section 9, we'll talk about how many, how probably, how about. And the standard deviation, which you may remember was 1.708, is going to be vital to that process. If you want to talk about how many, how probably, how about, you roll a die many, many times, you're probably going to get about 3.5. If you want to talk about how many, how probably, how about, then the 1.708 is going to be just as important as the 3.5. But long story short, we have talked about how to compute the standard deviation of a random variable. We've talked about how to compute the mean. We've talked very briefly in passing, half-heartedly, about how the mean of a random variable could be useful. We have not talked about that at all for standard deviation. How the mean and standard deviation of a random variable become useful, we will talk about in section 9. And we will quantify how many, how probably, how about. We'll put some math behind it. Why is that important? Because the law of large numbers is not hard to understand. It's a little jargony here, but it's not hard to understand. The average of what you do pick closes in on the average of what you could pick as you pick more and more and more of them. The average of what you do pick will probably be close to the average of what you could pick if you pick lots. How probably, how close, how lots. Section 9 has a way of confusing people when we get there. It's important to understand literally all we're doing is quantifying how many, how probably, how lots. How many, how probably, how about. So if you understand that all we're doing is putting a little math in section 9 behind this principle, then it will be a lot less intimidating when we get there. But obviously, there are a few things to do first. In section 6, Section 6 will be a series of afterthoughts and PSs to Section 5. It's just winding things up a bit. It's taking what we did in the last section and, in a broader sense, everything that we've done in all the previous sections, and kind of beginning to tie it together. So we'll talk about continuous random variables. We'll talk about unit changes. In a way similar to what we did at the end of Section 2, we'll talk about how to bypass having to compute all these things again if you do unit changes, lottery tickets and cents, profit on lottery tickets, things of that nature, and a few other odds and ends that will tie it all together. And from there, we'll be ready to go on to section 7, 8, and 9, which is the theory of statistics. The course takes a turn for the bizarre. So, like I said in the beginning, it is cumulative. We start off by averaging numbers together and drawing bar graphs, but it does get more complicated. Everything we're doing because it will help us to make sense of the stuff that comes later. So everything in sections 1 to 6 will help us to understand the concepts in sections 7, 8, and 9, which in turn will help us to understand the practical idea of how to use statistics starting in section 10 and forward. So logically, the course has 3 parts, and we're almost through the first part. Pick it up there, start in section 6 next time.